Good morning, friends. My plan here is a little different. I've gone through slide decks quite a few times. You may have seen my most recent category theory slide deck, a 40-minute presentation. The YouTube before this. I'm going to do a Flickr album instead, which is a repository of stills, so it's still very much like a slideshow. I share these slides with a purpose. I am always cultivating talent in the synergetics teaching realm, meaning I'm interested in spreading through other teachers, aside from myself, understanding and knowledge of synergetics, and that's Buckminster Fuller's synergetics. In case there's any ambiguity there. And this has been going on for a while in terms of my interests, and there are a lot of teachers out there. You just have to look for them. Casey House, David Koski, we've got a lot. Ben Lauder. Just do some searches. Joe Clinton. They go back, right? Because Bucky lived from the 1800s through till 1983, so he's a major figure in the 1900s. Now, what I should be starting to do here is looking at slides as we talk and showing off the kinds of things that I think will be characteristic of I'll call it Martian math class. Now, right away, that may be a turnoff. You don't want to talk about Martians. You don't believe in Martians. I'm saying an ET perspective, so an outsider view, a different math than we're used to. And one storyline that I've used with kids, like middle schoolers, is welcome to this training so that you'll be able to work with Martians on a hydroelectric dam project. There's this mesa somewhere, or maybe it's in Siberia now that I think of it, where the Martians have landed, they've set up a base camp, and they want to work with us Earthlings on something practical and productive, and that would be a hydropower dam, which is a somewhat new idea to them. I'm not saying there's really Martians, but you do know that Mars is a dry planet. They wouldn't have that knowledge there. Let's just say wherever they're from, the idea of damming a huge river and having that go through generators and make electricity is somewhat of a novel idea, and they want to learn all about it from us. But at the same time, they have a different math, which I'm starting to show here on the screen. Now, this is where I'll talk a little bit for a little bit on the actual slide. It says Ministry of Education in the upper left, and currency, and there's a picture of the sun and the earth getting flooded with currency on a daily, hourly, minute by minute basis. We call this the daily energy budget. You could think of the Lord's Prayer, give us this day our daily bread. It's our daily bread coming into the biosphere. And if you've read, or if you want to get a book related to this, I recommend a book called Into the Cool, which is about the thermodynamics of our economic situation, which is that we are on the receiving end of, you could say, grant income, which makes us really a nonprofit. Nonprofit economics is a good place to start, in that Earth is a nonprofit wholly dependent on its donor, the solar fusion plant we call the sun. So that's kind of a picture here. Now, this came out during Occupy Portland. You may remember there was a movement. There was little villages set up, non-sustainable, in downtown areas, including Portland. So we called ours Occupy Portland. And I self-created the Ministry of Education to go with that, since we were going to have, obviously, an alternative worldview and curriculum vis-a-vis what's currently promulgated. And so I created this Ministry of Education, and I based it, you'll see lower right, in the Washington High School here in Portland. I give it the date of 2012. Now, what's funny about this is the Washington High School at the time was all abandoned and boarded up and looked pretty ghostly, like there was nobody there, except there really was an artist colony or something like this. So I created this Ministry of Education as a ghostly abandoned building, which was entertaining. Now, you'll see circled in orange, somewhat cryptic looking, but once you can decode this, it will help you as a mnemonic, something to help you remember. You've got triangle, square, another square, it looks like. Anyway, these little like diamonds and stuff, those represent three-dimensional shapes like volumes. The one is the tetrahedron, T for tetrahedron. That's going to be our unit of volume. And so that's where the Martians are already being different from the Earthlings. So I tell the middle schoolers, the reason you're learning this alternative way of thinking about shapes and polyhedrons and volume and all this is so you can communicate with the Martians successfully. Of course, they know this is science fiction. It's not like they actually believe that this is going to happen, that there's real ETs in Siberia waiting for them. We know it's a story, right? But we want them to use their imaginations to help create the story. You could say maybe that robot there is one of the things Martians have brought with them. And these are quadrants of a tetrahedron facing us, made out of mites, again, building the namespace, building the shop talk. In the background is one of the food pulling trailers. You know, you can use that for kids, but at Food Not Bombs, we were always providing free food, using the surplus, excess, the waste. If you use it, it's not waste. That a big city generates. There's a lot of ways to hook that up and feed people that a lot of communities have banned. They don't think it's right for people to get free food. You really need to slave away somehow. You need to earn a living. That's how Earthlings think. That's a very alien concept to the Martians, that you have to earn the right to live. But you could see that. You could see that why Earthlings are that way. And they get very uptight if an organization like Food Not Bombs comes into a community and just starts feeding people in a public park. No means testing. It doesn't matter. We had a guy, really rich guy, who would bring his dog by private chauffeur and ask if he could feed his dog with our food. And I think they were just testing us to see what our boundaries were. And that was kind of crossing the line. We're really feeding humans first and foremost, but I could see a special program expanding to pets. Now, here's getting to be more realistic in terms of what actually did happen on Earth regarding new ways to live. That's a very lightweight sheet metal there, pounded together to make an interesting prefabricated house. It's not the kind of house we prefabricate today. We're still really obsessed on using wood for everything, right? Today's houses, not if they're apartments, maybe not, right? Most are freestanding houses, though, tend to be very wood-centric. And this is a good thing to introduce early. This is at the Henry Ford Museum in Dearborn, Michigan. Before you get too stuck on the stereotype of Bucky Fuller and geodesic domes, you got to realize that he had a whole career and focus on shelter. He owned Shelter magazine, trying to provide the world with easily assemblable, easily ownable, privacy-preserving dwelling machines, as he called them, that you wouldn't stress out about your financial situation. You wouldn't be having all that shouting and arguing that couples often get into over money and who's not pulling their weight and so on. He was thinking about family dynamics when he designed this, and how we could have a more happier adjusted population if we weren't, kind of living out our Protestant dream of you're a sinner if you're not a slave or whatever, whatever the earthlings think. This is what my backyard, looked like then. It's kind of similar today. And you can see that's C60. Well, you wouldn't know that, but those soccer balls lying around, that one in the foreground, or let's say the one with a lot of pink in it, it's not completely built, and it has a lot of broken members. The one in the background, it's all white. That's got less breaks in it. The C60 turns out to get pretty fragile in the sunlight. So we can talk about that. And those are Tibetan prayer flags across the top. Now, C60, that's a branded implementation of something the inventor calls flextegrity. And in the lower right is a whole different version of the same concept. And you can see there's kind of a XYZ perpendicularity. There's some regularity to this lattice, and it will be familiar to many as the CCP or FCC, or if you're into the buggy stuff, meaning you've done a little bit of homework, it's isotropic vector matrix, which we can also model as close as packed spheres, such as you see these little plastic guys. You could think of them as spheres. They actually have more shape to them than that. They have facets. By the way, the Book of Numbers by Conway and Guy, another syllabus book, put it on the shelf for getting the sequences involved here, right? What are the triangular numbers? What are the tetrahedral numbers? You can get the computer involved pretty early for doing these sequences. In the background, that loop-de-loop thing, that's from the Field Structure Institute. It's part of my collection of cool things. Now, do the Martians understand physics the way FSI shares it? I don't know, because that's not what I understand. So I'm the guy writing the Martian math curriculum here. So I collect these materials. I don't always have a lot going to go with them, but others might, right? You could have a different teacher who's really into the kind of particle physics aspect of Martian math, but I don't get into particle physics really, except for solar fusion and all that's related to electromagnetics, right? How that connects. We've got Synergetica Journal, that is very rare, and some artwork by Trevor Blake on the left. Synergetica Journal was a published pamphlet that had a lot of interesting, I wrote it, a lot of interesting synergetics in the early 90s. It helped us understand where we were at that time with synergetics in the secondary literature. Another artifact you're going to want to share is the Tetra book. Now, I'll just explain it quickly. It's like a book, but the covers are open flat on the table and are triangular. And then there's a one page, which you can see is more faded, more transparent, which, I drew this quickly, sketchily, so the lines don't really look that straight or whatever, but that's a straight-edged triangle page, piece of paper, you could say, that can flap back and forth. It can lie down on the left side and be congruent with that book cover. And then you take the tip and it draws a semicircle as it traces its path to the other side and lies down on that book cover. And in between, you get these stopping points where you've got different tetrahedra, like where it stopped right now is meant to show the regular tetrahedron comprised of the left side book cover, the page itself, and then an imaginary edge from the tip of the page to the book cover tip on the left, right? So all those lines, 6 of them, comprise a tetrahedron, a regular tetrahedron. Another position, though, that's going to be important is when the page is completely vertical. And the Martian math people, the teachers, the students, are going to know about this tetrabook, I believe. It's going to be helpful to them. This is looking down on a cube, except we've removed half the facets. And we're just looking at the corner of a cube from the inside. So it's like we're looking at the corner of a room, a typical room that's made of rectilinear walls and ceiling. That's what you would see, right, when you're looking up at the corner of a room, say. The 3 squares coming together, 90, 90, 90 degrees. However, on the lower left, you see a tetrahedron off to the side. It's got a lid that's kind of open. If you're looking at the very bottom of the picture there, you'll see that it's the same idea of 3 corners coming together, 60, 60, 60 in this case. And then there's a lid that's popped open a bit. We're going to be closing that lid sometimes, is how we say. And what's interesting partly is that the tetrahedron in the tetrabook, if the page is vertical, if the edges are all considered D, I'll say D for diameter. Think of a sphere and it has a diameter D. That could be the edge of both the book covers and the page itself. So half that edge length, D, is R for radius. Same sphere, same circle if we're doing circles. The radius is always half the diameter. So this cube in the upper left in this picture, it's all R edged. And that is going to be the same volume as this tetrabook with the page in the vertical position. You know, you'll have tetrahedron on both sides. I should have said earlier, too, that the complementary tetrahedron, where you take the tip of the page and draw an imaginary line to the other book cover. So in this case, there's a shorter and a longer edge to get to the corresponding book cover. Those two will have complementary same volume as each other, right? Same base times height, if that's how you're computing volume. And in this case, the R-edged cube up there is going to have the same volume as the vertical page position, where R is half of D. That's something interesting. There's some discussion of the tetrahedron made from zigzags, and the cube made from zigzags as well, right? The cube is made of 4 3-vector zigzags. If you can see that, it's maybe not totally clear. There's an orange, there's a green, and then there's 2 darker colors that seem to mix together. And nevertheless, you can get by 3-vector zigzags. By zigzags, I mean there's straight, bend, straight, bend, straight. So there's 3 times 4 equals 12, 12 edges, and so forth. Local Powell's, lots of magazines. Let's get some more magazines about math teaching and synergetics. Got a lot of art we could be putting in. Here's another picture of those cubes and tetrahedron, how they relate to each other. It turns out that the cube has a little bit greater volume than the D-edged tetrahedron. We put the exponent 3, though, to say we get a third power out of both of these. In other words, we'll say D to the third power. What the Martians say is that tetrahedron on the right with edges 2R has a volume of D to the third power. But that doesn't look like the third power the way we learn it in school. We learn third power in conjunction with a cube. That's why we say, instead of third power, we usually say cubed. Whereas the Martians look at us funny when we do that. It's like, what are you saying? So the relationship between the d to the third tetrahedron and the r to the third cube is it's a little smaller, so you got to multiply by the second root of 9/8, which is like 1.06066 times the tetrahedron gets you the volume of the cube. So Sesame Street, welcome to our Sesame Street. What I call the concentric hierarchy, or what Fuller also calls it that, what we call the concentric hierarchy, you could say it's the Sesame Street of synergetics. It's what you know your way around like the back of your hand to teach and learn synergetics. You understand about how we nest these polyhedra one inside another. And this would be our volume 3 cube made of 24 mites. They're magnetized. It's a very interesting toy that I can no longer find on Amazon. I found it in Britain. You could pay pounds for it. It's a very useful and important toy. I'm not sure that the people who make this toy understand its value for learning about synergetics. Here's a repeat with more visual of the tetrahedron in the lower left with the 60-60-60 corner and the lid open. Now here's the gist of it. This is going to be critical. How the Martians think about A times B times C. You know, like when we do multiplication height, width, depth, I give you ABC for the height, width, depth. You do a 90-90-90 degree corner, like we've been seeing with that cube. You multiply those three numbers together, and you get like a brick or a prism, something rectilinear, and that volume is going to be A times B times C. But what the Martians do, see here, this tetrahedron is all divided up into tetrahedrons and octahedrons. This is what we call the isotropic vector matrix. So all the green edges throughout this thing, they subdivide the tetrahedron that we're looking at, which is what we call a 5-frequency tetrahedron. It has 5 intervals between the white hubs. This is made in V-Zone, which is virtual zone, which is a computer rendering of Zone Tool, which is a plastic toy you can buy. But here we're doing it in the computer, so we have unlimited number of struts and hubs and stuff. And David Koski put this one together. And what we're showing here is 2 times 2 times 5. In other words, those 3 edge lengths, they all emanate from that same 60-60-60 degree corner that's facing us, that's closest to us, right? 60-60-60, meaning like the tetrahedron there on the left, regular tetrahedron. We don't go all the way to the far corners each time. We go only 2 units, so on the bottom there, flat, we're going 2 and 2, and that triangle you can see already has an area of 4. 4 triangles, not 4 squares. So you could say 2 to the second power equals 4, like we always do say. But what you're picturing in your mind's eye is not a square, but a triangle of 4 subtriangles. Now we can take the far left unit tetrahedron. We'll call it unit tetrahedron. It's just one green edge along each edge, right? So very close to us, closest to us, facing us is like, well, every tip of this tetrahedron actually has one of these unit volume tetrahedrons. Comparatively, the octahedrons that also participate in this skeleton have volume 4 times that of the tetrahedron. But we don't need to worry about the octahedrons, really. We're just thinking of the tetrahedrons as like cups as units of measure. When they say 6 cups of sugar, think of that unit tetrahedron as like a measuring cup. And you can fill it with sugar or rice or water, some kind of like malleable substance, so that we can understand about volume not having to have any particular shape. It's just however much of, it could be little beads or balls that fill space so we don't have gaps or something like this. Anyway, 2 times 2 times 5 would be the kind of the rib closest to us. All three of these edges emanate from the closest vertex. So 2 times 2 times 5, 5 is climbing up to the very top, define the internal tetrahedron, which we close the lid, you could say. We connect the endpoints of A, B, and C to create that sort of light-colored triangle as the sort of opposite facet from the 60-60-60 degree corner in the foreground. And it has all of these 6 edges, right? And its volume is what? It's going to be the same as in the cube world, 2 times 2 times 5, 20. So do I do a long proof at this point? Do I make that obvious? No, I leave it as a statement that you can question, verify, is it really true? But I'm going to say the Martians just take this for granted. Now let's go on. Other books you're going to want to have, maybe or maybe not. I recommend Who is Fourier on the right and Number by Gazelay especially. This is more two-dimensional and proving to ourselves that we can do these kinds of A times B equals AB in triangle world and not always use 90-degree corners like this. So this again is showing third power growth as this tetrahedron fills with water. It's a huge tetrahedron that the Martians have set up to collect water in the desert, I guess. There's an airstrip on the right for scale. And as the rains come, this thing fills. It's tethered to the ground with chains. It fills with water, and it's the progression 1, 8, 27, 64, 125. In Earthian math, we call those cubic numbers, but we call them tetrahedral numbers. We could say third power we think of in terms of tetrahedra. See, this is why our students need training, because they won't think spontaneously the way Martians do, because they go to Earth schools which are fixated on 90-degree angles in ways the Martians are not. This is actually the archive of Linus Pauling at Oregon State University, models he was making in order to better understand chemistry. And you see the closest packing of spheres, same thing we're into. In the background, those flags, these are places where I've had opportunities to share synergetics with students as I've traveled around the world. So you're starting to develop some familiarity now with all of these concepts. This one sums it up pretty well. This one I worked out in Bhutan for the Royal Kingdom of Bhutan. And it's just a simpler summary of some mathematical relationships relating to high frequency spheres, subdividing them. 3 frequency geodesic iconosphere, but you can go to any n, and there's Euler's law. Instead of spending a lot of time on this, I just want to show you as a teacher that it relates to modern chemistry. Buckminster fullerene is the name of a chemical made out of carbon atoms. Here again is our Tetra book, to some extent, made with this particular toy. So toys are going to be important, and volume is going to be important. This shape made of 4 hexagons, called the cuboctahedron, is going to be called the vector equilibrium if we change nuances. And, there's lots of things to discuss with Martian math, including the whole meme of Martians and how it permeates our culture. So we start to do historical investigation of the Martians as a meme, like that whole thing with Orson Welles and how he scared people silly with his realistic reading of War of the Worlds on CBS radio that time, Halloween. We studied that incident. We studied people's apprehensions about ETs and stuff and UFOs. It makes the math relevant, interesting, and gears it in with historical events and so forth. So this is an interesting drawing. It looks like there's a video called Damas about Fuller and going over a canyon and stuff, kind of primitive drawing, and this is similar in style. You go find what I'm talking about if you're interested, maybe. But on the left, we have the Martians. On the right, we have the Earthlings. And in the middle, that's the hydroelectric dam they're building. And you can see the wall of it starting to rise up. And we have the two sides of the gorge or the canyon that we are putting the dam across. And there's this crane across, which is taking concrete in buckets out over this wall, and the bucket here is a tetrahedron full of concrete. So how much concrete is it, and how do the Earthlings and the Martians agree on, what is the conversion constant and so forth? And that's where we introduce the synergetics constant and so forth. So here we have the Martians kind of segregated with their own campus. Turns out that, a lot of Earthlings don't like it that there's Martians on the planet and that we're collaborating with them. So there's some degree of protecting them. You see the gorge in the foreground. You see the dam that's being built, or maybe it looks kind of finished in this case. These are just kind of off the top of my head, sort of stream of consciousness. And I'm expecting people who adopt this idea, which I'm putting out in the sort of public domain, to make changes. It's like we got some vodka there in the background. That makes me think we're back in Siberia with this dam, maybe with the Russians helping us talk to the Martians. In fact, maybe this whole curriculum is going to emerge in Russia first and might actually be well along in that context. I'm not directly working with Russian schools, but out here in Cascadia, we have a lot of Russians, a lot of Russian speakers. So it wouldn't surprise me at all if some of this has percolated by osmosis back to Siberia and places like that, where we could actually be building dams, right? So that does go on with or without Martians. And the global grid concepts and so forth, you'll see there's a lot of square root or second root of 8/9 and 9/8. You've been seeing that if you're watching. You're seeing how this fits together in kind of a comic book. I recommend doing storyboards in the form of comic book. All this second root of 8/9, 9/8, that's all going back and forth between Earthian and Martian systems of volume, what we call the synergetics constant. You'll see, again, reiteration of the importance of certain toys. This, again, is back to Occupy. And this I'll dwell on for a second. We are looking at the platonics, that P for pentagonal, C for cube. These are actually symbols for three-dimensional shapes, the so-called platonic polyhedra. And they're duals of each other. Like the cube and octahedron, you see an orange line connecting the square and another square on its side. That's CO. Computer pictures might be more clear, but with drawings by hand, you can say it's more human friendly. You could put this on chalkboard and stuff. Use colored chalk or whiteboards. So pairs of duals like the icosahedron and the pentagonal dodecahedron, when you combine them such that their edges crisscross at 90 degrees, you get these rhombics from those. So our Genesis story, we start with the platonics, which is where a lot of people start when they're teaching 3D geometry, but we are taking it towards the duals and then towards combining duals to get the rhombic dodecahedron and the rhombic trichontahedron. and the tetrahedron dualed with itself and combined makes the cube. So dual pair beget. We have Genesis because when we put these duals together, they beget a rhombic shape, or a polyhedron with rhombic faces, a rhombohedron of some kind, like the rhombic dodecahedron. A favorite of Kepler's because it fills space, right? So some redundancy here. You're starting to appreciate the themes, flextegrity. Now, you may not be able to get your hands on flextegrity for your version of this course, but then there's pictures of it you're welcome to use here in this slide. The Martian math aspect, that was Marvin the Martian. I keep going back to these alternative pictures of multiplication. There's another drawing of the two sides of the gorge and the Martians versus the Earthlings. This is a whiteboard at the Linus Pauling house. That Linus Pauling also went to Washington High School, the one that was abandoned at the beginning of this slideshow. It has been reopened, by the way, and the first thing they did was debut a show about Buckminster Fuller. It was called Love Song for Buckminster Fuller. The director of a film comes to town, and with an orchestra or a famous music group, Yole Tango, something like this, right? They play the music, he narrates through the movie. It all happened at the Washington School, and ever since it's been a fancy venue. Now it's called Revolution Hall. So don't dismiss Occupy as being a relevant footnote. It was more boosted us across the threshold, I would say, to where now in Cascadia, which is where I live, this kind of thinking is catching on and spreading around, and more students will be asking their teachers, what can you tell us about Martian math? So here again, Saturday Academy has been involved, Reed College, right? I've been doing this for a long time, and we have a lot of talent in this part of the world, right? By Cascadia, the borders are not fixed. I go all the way down into California. Crescent City's a hub. Seattle's a hub. So there's our D-edged tetrahedron, vis-a-vis our R-edged cube. Remember that cube, even though the edges are only half as long, has a little bit bigger volume than the tetrahedron, the Martian tetrahedron. Keep going back to the study of the Mars meme. Keep talking about area and volume and toys and the desktop you might want. So you're getting the themes now. I'm speeding up because familiarity is increasing, I'm hoping. The A and the B modules, been doing this for a long time. Core to synergetics are these tetrahedral wedges which we use to assemble the Sesame Street concentric hierarchy that we all know about, back to Linus Pauling's archive at OSU. These are more technical, more difficult in some ways. I won't go into great detail except to say we are filling space with tetrahedrons, octahedrons, and we're getting into something called quadrays. Now, when you build a whole hydroelectric power dam, right, then you're not just doing like a battery and a light bulb and a little switch. This is how we often start teaching about electricity, and I'm not saying it's either or, but we definitely want the large scale in the picture, the global grid. We're talking about long lines. We're talking about high voltage DC. We're talking about the story of grids and their interconnectivity, interconnections, or lack thereof. If you saw my category theory slide deck, this is King Hilbert again, bringing in machine learning, and Demeus, that guy, and the idea of namespaces also in category theory, but you could call it scion, the little what's on called 4D, four-dimensional, that particle of meaning. It doesn't have the same trajectory in these three different namespaces. The one of polytopes and Coxeter, that's closer to Hilbert space and machine learning, that whole very successful corpus that's helping us generate um, new imagery and so forth, and text. That's the 4D of polytopes, Coxeter, extended Euclideanism. As many spatial dimensions as you want. We call them mutually independent, meaning perpendicular, orthogonal, and then we say we can't visualize that, of course. 10 mutually perpendicular axes we can't visualize, but sometimes we pretend that other beings can, maybe. And then we've got the 4D in Einstein, which is 3D plus time and like that. It's a different algebra, it's a different math. And then 4D that we're studying here as Martian math is yet another meaning of 4D that Fuller branded around his whole life, really. This was an AI generated picture where it decided the Martians were pretty big and was trying to have them explaining the 60-60 degree stuff to the Earthlings there, who are relatively small in the foreground. The dam looks pretty finished in the background. And are we even on Earth with that giant moon in the background? Very interesting graphics, I think. Some of the people just don't have any patience for AI generated graphics, but I think they're fantastic sometimes. This is a very strange dam, the way it holds back the water coming from two forks, from two places. Don't know if that's ever done or why anyone would do that, but it's just kind of interesting. So obviously the whole idea of hydroelectric and making hydroelectric power is integral to the Martian math syllabus. So I think that gives you the flavor, and as a teacher, if you're a teacher, take these memes and run with it as you would like. I have collaborators who have been doing things like this, and as you can see, they've been helping me with some of this graphics ideas, models. Not everyone who makes toys in this area realizes the value of their own toy vis-a-vis this particular curriculum. So ordering those toys, especially that magnetic cube, this one, might help them understand the market better that they're serving. That cube octahedron up there on the left of orange and red facets, that was actually designed by Kenneth Snelson. It fits around a sponge or something soft of the same shape, and I still have the sponge, but I can't find those facets right now. They may have been lost. I've been doing this for a long time, so some of the toys come and go, but the Kenneth Snelson one I hope I still have, because he's a good friend, and we had a lot of interesting discussions about some of this material. All right, so let me end on this slide. This is kind of how I connected together the CIA between Grunch of Giants and Transcendentalism. If you pick up on that, has to do with Ed Applewhite, features in other slide decks that I have, but he was Bucky's close collaborator, and it's like the deep state is not unaware of all this, and therefore think of this as a prerequisite. Like, if you don't know synergetics, just don't think you can ever be in the CIA. There's no chance. No chance. Okay, so there we go. Interesting stuff. I hope you follow the link down there in the description, which will take you to this album. And send me any questions, and we'll talk again.